Password recovery. Cisco's password recovery process isn't something you will need frequently as a network engineer, but a familiarity with the process will prove valuable in a time of emergency. In this nugget, we're going to recover and change all the passwords in a router, but before we can complete that process, we'll have to introduce a few new ideas. And we're going to start off by looking at the connectivity involved, the devices we use, the cabling, and the software packages. Then we'll talk about ROM monitor mode. What is it, and how do we use it? Followed by a detailed look at the configuration register. Access to the Cisco router can be accomplished with many different terminal emulators, each with a different break sequence. We're going to look at a few of the most popular break sequences in this portion of the nugget. And once we've completed all those tasks, we're going to move forward into our password recovery procedure. Connectivity starts with the idea of connecting a terminal or terminal emulator to a Cisco device. Let's talk about terminals first. Terminals used to be dedicated devices designed to communicate directly with a network device. What happens now is there are software packages that can reside on a PC called terminal emulators that can accomplish the same task. And that's more than likely what you will be using. In fact, one of the terminal emulators that comes free with the Windows environment is HyperTerminal, and we're going to discuss it in more detail later in this nugget. All right, so let's get back to our basic idea. We want to connect out of this device, and the way we're going to do that is a communications port. On the back of every PC, you have one or more communications ports. They are normally 9-pin connectors, and you call those DB9 connectors. Cisco is going to provide you with a DB9 connector that looks like this, 9-pin female on this end, and on the back end, space for an RJ45 connector. That's the one that looks like a phone jack, but it's a bit larger to plug into the back of this adapter. Once this connector is in place, we're going to need something to bridge the distance from that adapter over to our router. And what we use is a Cisco-provided rollover cable. Now this rollover cable is called a rollover cable because it has 8 slots within this RJ45 connector. You see 1, 2, 3, 4, 5, 6, 7, 8. A different color wire will be in each slot. Let's say that in slot 1 we have a green wire. That means that in the other corresponding RJ45 connector on the other end of the cable, that green wire will be in slot 8. If you have a brown wire in slot 2, that brown will be in slot 7. And that'll continue up until you get to, let's say, a yellow wire in 8. That will be in slot number 1. The wires are completely rolled over. It will be a mirror image. And so now we're ready to connect our COM port to this adapter into this rollover cable and bring it to the router. Here I have the back of a 2514 router. Now there's many devices that you can connect to, but I just wanted to use this as an example. We have many receptacles. First we have the power running out of the wall into here. We also have AUI connections. These are used for Ethernet. In the cases of other routers or switches, you will see RJ45 female receptacles that you can plug those connectors into, similar to the one that you have in the back of this adapter. We also have support for serial cables here. And then now finally we get to the console port and the auxiliary port. We're going to connect here in our console port. Let's review what we have so far. We'll connect our adapter here. We will run the Cisco provided rollover cable over to the Cisco router and plug it into the console port. We're completed if the back of your device that you want to console into has an RJ45 connector, and they're female connectors. But sometimes you're going to run into devices that support a DB25 connector. Simply put, we have a 9-pin here. A DB25 will have 25 pins available within the connector interface. When that's the case, Cisco will provide you with an adapter that has the 25-pin connectors here, and on the back end of that adapter, again, the RJ45 receptacle, so that we can plug this cable into the back and then plug this portion into our console area. Now that we have a good understanding of the physical connectors involved, let's see what happens electrically. First of all, let me set your bearings. We're going to have on this side signals associated with our router. That is sometimes referred to as a DTE device in different literature. And then on this other side, the signals associated with our PC, also known as the DCE device. This can be, again, remember, a PC running terminal emulation software or an actual terminal. All right, let's see what we have. Remember, coming out of our console port on the Cisco 2514, for our example, we had an RJ45 connector directly into the console port. And we also had that cable, the rollover cable, running, terminating at another RJ45 connector. Here are the number for each associated wire on those connectors. Here's the signals associated. What we're trying to do is get RTS, request to send, DTR, data terminal ready. We're trying to transmit data. We have 2 grounds. We're trying to receive data, and then we're sending other signals with data set ready or clear to send. All right, so when we do that, this handshake has to take place. All that the RJ45 cable is going to do is roll everything over, because remember, it's called the rollover cable. So what we're going to see is pin number 1, as we said before, going down to the 8th position. Pin number 8 going up to the 1st position. So these are crossing. So 1 to 8, 2 to 7, 3 to 6, 4 to 5, and so on. Once we get out of this cable, we can either terminate on a DB9 or a DB25 at the PC end. We're going to mark this up and say we're going to terminate with a DB9 on a COM port. Signal 8 from that RJ45 goes to 8. 7 to 6, 6 to 2, 5 to 5, 4 to 5, 3 to 3, 2 to 4, and 1 to 7. And essentially what we're doing is when we transmit data, when it arrives at our PC on the other end, it's received data. When we transmit data from the PC over to our Cisco device, that's the receive pair for the data. All right? And then clear to send has a corresponding request to send. And up here, if we request to send, we can answer saying clear to send. All right, so with the DB9 connector, these are the pins associated with each of the signals. So what if we're using a DB25 connector? Let's do this. Let's mark out the DB9. And now you see here, 8 to 5, 7 to 6, 6 to 3. You won't have to know this on a daily basis, but it is very good to know for troubleshooting purposes, or if you have a myriad of connectors and you're not sure which one you're supposed to use, you can simply run the test or run signals through those connectors and make sure they come out in the correct pin. Now that we've covered the devices and the cabling associated with connectivity, let's take a look at the software packages that we were talking about, the terminal emulation software packages. They're going to enable our PC to appear as a terminal to the Cisco device. What's going to be important here is a couple of settings, the baud rate, the parity, the data bits, and the stop bits. But before we define what those need to be, let's look at packages available. The first one is going to be HyperTerminal. This comes with Windows as a free software, and it is used as a terminal emulator. Let's run into that program first. Going to Programs, it's stored under Accessories in the Communications file, HyperTerminal. The first thing it's going to ask you for is a name of a session. We're going to label it console. That can be any name you want it to be. Now it's going to ask you which COM port do you want me to use to connect. You can use COM1 or COM2, and also an availability is there for TCP/IP WinSockets, which will not be used to connect to a console. So COM1 or 2. In this instance, I'm going to opt for COM1. Now, once you do that, this is where we have the information that we need to put in. The bits per second, the data bits, the parity, and the stop bits. We're going to run at 9600 bits per second, 8 bits on data. Parity is none. You see the options here. You can go odd, even, mark, or space. We're going to stick with none. The stop bits, there's options there as well, but we stay with 1. Leave flow control as hardware, and then just simply hit OK. Once you do that, you press Enter, and you're going to get your router prompt. Now we have full connectivity to the router via the console, just as we depicted it on our whiteboards right here, from our COM port into our console port. So let's mark down what we've discovered. Our baud rate is going to be 9600. Our parity is none. Our data bits that we're going to use is 8, and our stop bits are set at 1. This is going to be true of every terminal emulator that we configure to connect to a Cisco device. These will always be the same settings. Now we're going to go into another option. It's called Secure CRT. It is not the basic package that you're going to find in HyperTerminal, but it offers a few more bells and whistles. Connectivity using Secure CRT is going to be accomplished using the Quick Connect method that we see here. I hit Enter, and I see my protocol choices to be Secure Shell, Telnet, R-Login, Serial, and TAPI. We're going to opt for Serial because the console connections that we're making are asynchronous serial connections. All right, the port COM1. Again, we have many other ports that we can choose from as far as COM ports. We're going to opt for COM1, baud rate 9600, data 8, parity none, and stop bits 1. I'm going to hit Connect, but when I do this, we're going to get an error, and I'll tell you why. Access is denied to COM1. That's because we still have HyperTerminal running and connected to the router. So we can run two different terminal emulation packages on the same PC, but we can't use the same COM port for both packages. Let me exit out of here. All right, now what else? I'm going to close this terminal emulation on HyperTerminal, and it's going to say something interesting. Even though I exit out of the router in the background, it says you're currently connected. Are you sure you want to disconnect now? So even though I don't have a router prompt here, it's still connected to that router. So say yes. That way to close it out. Do not save. And now let's go back to our secure CRT, to our Quick Connect, and make our connection now. Hit enter at the prompt, and there we go. Now we're into our router. Don't you love it when a plan comes together like that? Now that we're done with connectivity, we're going to move into studying ROM monitor mode. All right, let's talk about it. It's a low-level problem determination mode. It's really analogous to safe mode in a Windows environment. As you know, with safe mode, when you can't boot up to the regular running mode, you have this mode that you get into that allows you to try to troubleshoot the problem and fix the problem so that you can get where you need to be. Same thing with ROM monitor. Now, ROM monitor, as the name suggests, is actually running in read-only memory. So let's say this is the space of read-only memory. There is this mode of ROM-mon. And to save confusion, and this confuses a lot of people, there also is a small iOS in ROM as well. That's called the boot image. And whenever you're running in that boot image, you're in what is called RX boot mode. So don't confuse the two. They both run out of ROM, but one is an iOS image or a subset of the iOS, and another is simply a mode when you have no iOS available. Let me run an analogy for you. Let's say I have two mountains here. Funny looking mountains, right? All right, your objective is to cross these mountains. I'm going to have a rope bridge suspended here. All right. I also have a net beneath the rope bridge to serve as another fail-safe. Underneath that, we have some raging waters that are ice cold. All right. Under normal operations, you want to cross this bridge here, and that would represent our normal operations on the router. If for some reason you can't find a valid iOS, to keep the analogy going, you're going to fall down into what's known as RX boot. This is where we have a subset of our iOS. We can continue to go across. It's not as easy as it would have been here walking over that net, but it's still much easier than the alternatives. If for some reason we have a hardware problem, and that's the normal cause of not being able to access the RX boot prompt, then we would be into ROM monitor mode, which for our analogy would be swimming through the icy water. We're still progressing. We still make headway to our final destination. It's just not the optimal path. All right, now with ROM monitor mode, after I do this analogy where it seems accidental that you might wind up there, with password recovery, we actually go into ROM monitor mode on purpose, and I'll explain why. Within ROM monitor mode, we're lacking an IOS, the Internet Network Operating System for Cisco. And as we said that, it is aware of a configuration file. Now we're going to work with configuration files more in depth in a later nugget, but a configuration file simply stores all the configurable data for that operating system to run. It's aware of this file, but it only runs a low-level or subset mode of commands and instructions. And part of what it leaves out is the passwords needed within this configuration file to get between the two levels. We have a user exec level in a router where you're pretty much, your hands are tied. You can do many show commands, but that's all you can do. And then beyond that, we have the privilege exec level. In that privilege exec level, we are able to get into configuration mode and make changes to our configuration file. In the configuration file is where we store passwords. And when we're in ROM-mon, to get between these two levels, no password is needed. That's why ROM monitor mode will be very important to us in our procedures for recovering the password. Although there are many accidental ways to arrive at ROM monitor mode that include hardware failure or losing or corrupting an image file for the iOS, we need to talk about how we can get there purposely. And the way we do that is by manipulating the configuration register. As you can see, the configuration register has 16 place values from 0 to 15. And they're grouped in fours: 0, 1, 2, and 3 in one group, 4 through 7 in another, 8 through 11, and then finally 12 through 15. Each of these bits have a significance and a significant action in the configuration registry. We're going to cover a few of them, the more important ones. First of all, we're going to look at this one down here, the number 1, this place here. If that bit is turned on, we're going to operate in what's called normal operation. In other words, it's going to look for an iOS image where it normally would look for it. All right? Now, if we had all that bit turned off and all of the other 3 in this section of 4 that is called the boot field, then we would result in a 0, and you would stay at a bootstrap prompt. All right? If for any reason we had just this first, the 0 option here, turned on only, it would result in a 1, then we would load the iOS in ROM. Now, I don't want there to be any confusion in the numbers I'm writing here, so let me go into a brief explanation as to how we derive at these numbers. All right, 3, 2, 1, and 0. These are bits. The 0 bit, the 1 bit, the 2 bit, and the 3 bit. They have associated values with them. If the 0 bit is turned on, it has a value of 1. If it's turned off, it's 0. If the 1 bit is turned on, it has a value of 2. If it's turned off, it's 0. The 2 bit, if turned on, has a value of 4. Turned off, 0. The 3 bit has a value of 8. If it's turned off, it will be 0. All right, so you get an idea here that we're incrementing or multiplying by 2. 1, 2, 4, 8, and this is called the binary number system. We're going to cover it in more detail in later nuggets, but for now, just accept the fact that each of these place values has an associated value if that place is turned on, and associated value if it's turned off. So, in the case of turning the 1 place on, the result is a value of 2, which means normal operation. If we turn none of these on, they're all zeros, then I have a bootstrap prompt. If I turn on just this value, so the result would be off, 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 and this on, then I load the iOS that's in ROM. And this is the RX boot mode that we had talked about earlier. That same formula is going to hold true in every other section of 4 place values that we have here. So let me take another example. Let's say now that we're going to work with 7, 6, 5, and 4, which are these place values here. They have the same values. If this number 4 is turned on, it's a 1. If number 5 is turned on, it's a 2. If number 6 is turned on, it's a 4. Number 7 is an 8. All right, so in the second section, let's say that we simply turned on this value, the 8 value, and turned the other 3 off. What we would have as a value there in total is 8. And here, let's say that we opted for this last example that we showed, where these 3 are off and the 1 is on, then we'd have 1. So this would be represented as 8, 1. It wouldn't be a matter of running them together, so it would be 9, simply 8, 1. And as we do that, for all 4 of the sections, we will have a value for the configuration register that is understood within the configuration file. Let's continue on and look at some more important placeholders. 6 now, which is this one here, is where we can opt to ignore NVRAM. What does that mean to us? When we ignore NVRAM, we are ignoring the configuration files. This is ROM monitor mode is the result. And this is what we're going to enter into for password recovery. So we've got to remember that we're going to turn this specific value on when it comes time to change the configuration mode so we can recover our passwords. The next important place value is the 8 value, which we find here. If activated, it disables the break sequence so that we can break the system boot up on our router. All right, the next values we want to look at are 11 and 12. We find them here and here. These are important because they set the baud rate on our console connection. If you'll remember, we opted in our settings for 9600 when connecting to our router as a baud rate. What that is that's the value if 12 and 11 are both zeros. Okay, so that's 9600. In fact, let me finish out this table for you. 0 and 1 together, that's going to be 4800. 1 and a 0 is going to be 1200. And then 1 and 1 together results in 2400. This is the speed, the baud rate at which we make our connections. Why is this important? In some cases, you may have a terminal emulation software on your PC that has a bug in it, or for some reason is having trouble connecting to your Cisco device at 9600. One thing you can try if you're having those problems is come into the configuration register and set it for one of these other 3 settings, and then change the parameters on your terminal emulation and try to connect that way. And you might find success, and it's simply attributed to a bug. And it's not unheard of. It's happened before in HyperTerminal and a couple of other software packages as well. The last value that I really want to cover right here, so place value is 13. This is a control that allows us to boot default ROM software if netboot fails. Okay, when we have an operation down here in the boot field of 2 and it says normal operation, that's what's called a netboot. That's this area here. If for some reason that fails, we want to move into the small iOS that we have in ROM, and this bit in the register is what allows us to do that. Remember when we talked about ROM, we had ROM on as a mode, a low-level mode, but then also we had that iOS in there, a subset of the iOS with few commands. That's what is allowed if this bit is set to on. So there we have the actions associated with the more significant place values, and we also have an understanding as to how we're going to represent the configuration register. It's a 4-character, it's alphanumeric value to represent 4 place values at a time, or 4 bits of the place value at a time. So we could have a result, as we said earlier, of 0, 0, 8, 1, if this was the only place value turned on, and this was as well. All right, so let me tell you though, in most routers, what you're going to have as a default for the configuration register is 2102 under normal operation. So let's see what this turns on. First of all, this first value of 2 has to be in this grouping of 4. And this is the 1, here's the 2's place. So 13 is turned on. So by default, normally we have the boot default ROM software image if netboot fails turned on. All right, so that's good. We have that option open. Now the 1, that has to do with these 4 places. That means the 8th value, which is the 1, is turned on. We disable the break. 0, that means that these place values, none of them are turned on, have no values. And then we end up with a 2, which turns on this place value, and that means that we're going to have a boot field result of normal operation. All right, now that we know how it's represented and the actions associated with a couple of the place values, let's move into how we make changes to the configuration file. And the way we do that is with a command called config-register, and then we're going to have a space. And this is going to be the interesting part. We know we can set a value, like we set in a normal operation of 2102, but when you represent that to the configuration file inside the iOS, Cisco starts out with 0x and then puts in that value, 2102. All right, and this value here is written in hexadecimal. So far, we've activated the numbers that will result in something that is equal to a representation, whether we had it in decimal or hexadecimal. But now we're going to cover how they differ and how we would go about representing the configuration register in hexadecimal differently than you would in decimal. Let's take our group of 4 values. Remember, the first place value had a 1, the second a value of 2, the third a value of 4, and the fourth a value of 8. If we had all of these turned on, every single one of them, we would have values of 8 plus 4 plus 2 plus 1, which would equal 15. Okay, so the highest value we can have is 15 within this 4 place value subset. And the lowest we can have, obviously, is if they were all turned off and we had a 0. Right? So between 15 and 0. So let's write that in decimal form. We got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay? Now let's write their hexadecimal equivalent. We have 0, 1, and you're going to find for the first digits that they don't change. In fact, up to number 9, they are the same. Now the problem is in hex, you have 1 character to indicate the value. Okay, you can't use 2 as you do here because it'll cause confusion. So as soon as we get to the 10, the character they choose to represent 10 with is A. 11 is B, 12 is C, 13 is D, 14 is E, and then 15 is F. Okay, this is our hexadecimal structure. Okay, so now that we know that, if for some reason we had a value of, let's keep the 21, 0 as it is normally, and then here we activated this value and this value. That would result in a decimal 10. That's going to be represented in hexadecimal as an A. So if we wanted to change that in the configuration file, we would represent config-register space 0x210A. And the result of that would be the normal operation of the boot here, and then whatever action is associated with turning this place value on. All right, and that can happen anywhere throughout this file. If we wanted to represent here, turning this value on, this value, and this value, that is 8, 2, and 1, comes up to be a decimal 11. That is a B in hexadecimal. So we would have the regular 2 as we had, B, 0, alpha now. All right, so you get the hang of it. If for any reason these concepts haven't sunk in fully, don't worry about it. Understand that in our password recovery, there's simply going to be an instruction that says change the configuration register from the normal 0 by 2102 over to 0 by, 2142. And I simply give you this information so you have an understanding as to why we're changing what normally is a 0 in this second 4 place value area into a 4. And if we go back a slide, we discover that that place value is this 6th place value, and here it results in ignoring NVRAM and moving us into ROM monitor mode so we can perform our password recovery. So far in this nugget, we've looked at connectivity, we've looked at the ROM monitor mode and what it is, we've even broke out in detail the configuration register and how we make changes to it. The next thing we're going to look at is the break sequence. The break sequence is very important because depending on which type of terminal emulation you're using, the break sequence is different. Let me give you some examples here. I have HyperTerminal, Secure CRT, TeraTerm, VT100, and Kermit. I even have an example of telnetting to the Cisco router. To issue a break sequence, you use different keys depending on which software package you're using. Let's step back a moment and talk about exactly what a break sequence is. Whenever you power cycle a router, that means turn it off and turn it on, it's going to go through a boot process. As it's booting up, if you interrupt that process here with a break sequence, depending on the package you're running, these keys, then you're going to be able to move directly into another mode of operation. In this case, it's the ROM monitor mode without iOS, and this is where we're going to make our changes to the configuration so we can restore the password in some cases, and in others, change it so that we can gain access into that router or whatever the Cisco device is. All right, so let's take a look at HyperTerminal and Secure CRT. Both use the same break sequence. It's a control key coupled with the break key. In Telnet, control with the side bracket. In TeraTerm, Alt-B. In the VT100 emulation, it's simply the function key 16. And then finally in Kermit, it's control backspace L. All right, there's going to be, for sure, some other emulation packages that you may use. And if you do use them, just simply look at the documentation with that package to find out the break sequence, okay? Cisco doesn't really report break sequences for these third-party softwares. They'll give you some of the more popular brands and give you the answer to those. If for any reason you cannot find out the break sequence to your software package, there is an out, and we see it down here. I'm running terminal emulation here and a Cisco device here. If I set my baud rate to 1200, parity to none, data to 8, stop to 1, in other words, I'm just simply changing this baud rate. Power cycle the router, turn it off and turn it on, hold the space bar down for 15 seconds, then disconnect from my router, set this back to 9600 as it should have been, and connect to that router again via console, then this space bar being held down at that baud rate simulates the break sequence. Okay, so you don't have to have these specific keys. Of course, this is more trouble and it takes more time than if you did have them. So optimally, you would have the break sequence, and you would use it in your recovery procedures. Excellent. Now that we have a solid understanding of all the components involved, let's put them together and make the magic we call password recovery. Here are the steps involved in password recovery. As you can tell, there are 12. I couldn't resist. Password recovery is a 12-step program. I'm also going to bring up the router. All right, I am at the user exec prompt of my router. Looking at the steps, the first thing I'm going to do is power cycle. Turn it off, then turn it on, and then initiate the break sequence within the first 60 seconds of the boot up. Let's do that first. You're not going to be able to see me turn the router on and off, but you will see the results. That's off. That's on. Now as it starts to boot, I'm going to hit the control and the brake keys simultaneously, and it's going to result in this prompt here, and it aborted the boot sequence. So what's the next thing we do? We're going to change the configuration register, change bit number 6 to a value of 1. In other words, going from 2102 to 2142 like we talked about earlier. And there's a couple of ways to do this. It depends on the type of router you're on. If you're on a 1600, 2600, 3600, 4500, or 7200, or even the large 7500, you do it with a CONF REG command. Let me write that down for you back here in the back. Okay, it's CONF REG. So that's confreg, and then you put in the desired value, which would be the 2104 or 2142. Now for us, we're in a 2500 series router. So for the 2000s, 2500, 3000, 4000, and the 7000 series, we're going to issue a different command. And that command is right here. Get it clear. O/R space 0, this is the number, small or lowercase x, 2142, and then you simply hit enter. Alright, so that is going to take care of changing that registry for you. The next thing we're going to do, if I slide this window down a bit, is we're going to software restart. And what does that mean to us? It means I can't power cycle the box with the on-off switch as I did before. You have to cycle it with a software command. Two options again. Some routers are going to ask you for a reload command. The 2500 series is going to ask you for an initialize command. Understand that either one is going to result in the reload, and these are the only two steps that are different depending on the platform that you're running. Okay, let me write it to the side here. It's the 1600, 2600, 3600, you're getting a pattern there, aren't you? The 4500, 7200, and 7500, they're in the first group of commands. In other words, the confreg is for that set of routers, and so is the reload. Now the 2500 series, coupled with the 2000, the 3000, 4000, and 7000, use the second series of commands. This was O/R space 0 by, and then the configuration register you want to set, which in this case is 2142, and in here for the software reset is initialized. Everything else from this point forward is going to be exactly the same. Let's go back to our router, and we will initialize at this point. All right, this is going to take some time because you're rebooting the router, and it's a slow process as it goes through the boot image and quite a few other things. So as we're waiting, we're going to talk about the next step that's coming up. Right here in step number 5, we're going to decline the setup mode. What does that mean? First of all, let's start with an explanation of what the setup mode is. Let's get onto that screen. Setup mode is a quick start application that says as soon as the router comes up, if it finds no configuration file within NVRAM, which it won't in this case as you're coming from ROM on initializing, it says I can ask you a series of questions and get this started very quickly, like do you want to turn on IP? Do you want to turn on IPX? Do you want certain routing protocols? Can I turn interfaces on? It's going to go through this dialog, and all you have to do is simply answer these questions. At the end, it's going to have a command config that it puts together and ask you, do you want to use this configuration? It's a very handy tool when you first start up a router or when you're delivering it out to a site to be deployed. But for now, we are going to decline, in other words, say no to setup mode so that we can move forward with gathering the passwords. Let's look back on our router. Okay, here we have it. It's still in the boot process. So let me exit off here and I'll come back. Oh, actually, there it is. Would you like to enter the initial configuration dialog? This is where we answer absolutely not. Press return to get started. What you're going to see now is the interfaces going up and down. When you initially start a router, the interfaces jump in the up state. I guess it's just an optimist at nature. It says these interfaces are up. It soon finds out that they're administratively down. In other words, I've set them to shut down, so it has to report that as well, and that's why you see the change of state to down. All right, now that we're in the router, the next step is enter the privilege exec mode. This is going to happen the same regardless of the platform you're on. We use the enable command. And then we're there. Did you notice it didn't prompt us for a password? This is what we were saying is the value of ROM-MON. We still have the initial config that we had before, but it doesn't apply the password. So to get from one level to the other, we don't need a password, which is great because now I'm going to go on to the next step and show the startup config. So show start config. Once I do that, I am going to do exactly what it says. I'm going to change the encrypted passwords, and at the same time, when I'm showing the startup config, the reason I'm doing that is I'm going to take note of any passwords that are not encrypted and write them down. Okay, let me open my window a bit so we can see better on the configuration mode. All right, the first thing I see is the enable secret. It is encrypted, so obviously I can't write that down. We're going to have to change that. It does not have a regular enable password, or we would see it here. There's options for the password: enable secret, the enable password, and then the user exec password is going to be applied depending on what type of connection you're coming in on. I'm going to hit the space bar so we can see the rest of the configuration and see if that password is indeed set. And here we go. We have line console, line aux, and line VTY. Recalling from an earlier nugget, these are the three opportunities we have to connect into our router. And line console has no password set, so we're clear there. So the only thing we have to do now is configure a new password for the enable secret. And we're going to see that as our next step here. Change the encrypted passwords. How do we do that? We're going to have to get into config mode. We're already at the privilege exec, so now I'm going to configure from terminal. Once I'm in there, I am going to use the command enable secret, and 0, I put that number in there because in the syntax of this command, this indicates that what's going to follow is an unencrypted password. You could use a different number and type in an encrypted password if you had that available, but we don't. So I'm going to type in Cisco at this point right here. Enable secret 0, it's unencrypted, is Cisco. Okay. Once we do that, we're going to Control Z to get out of the configuration mode. How did I know Control Z? Right here. End with Control Z for the configuration mode. It gives you a little message that you configured from the console by the console. You can simply hit enter there to get to your next prompt. Now we've changed the passwords. The next thing we need to do is change the configuration registry back to 0x2102. Okay, so that takes another trip into the configuration. Now what I wanted to do is jump out so that I can show you that my up arrow keys, as we've talked about in an earlier nugget, will get me right there to the command I needed. Configure from terminal, jump in, and then we're going to change the config register. The command is config-register 0 lowercase x 2102. Hit enter there. Control Z to get out of this again. And now the next step, the 10th step, we're almost there. Save our configuration to NVRAM, because as we write it in this configuration mode, we've saved it into RAM, which is our running config. That is not permanent. So if we were to reboot, which we're going to do in our next step, we would lose this configuration that we just changed. So what we're going to do is issue a command. It's called copy. You start off with the from. We're starting from the running config, and we're going to copy that into the startup config. All right, and then ask you, the destination file name, startup config? Yeah, that'll do it. All right, it's going to take a moment to build the configuration. As we said, once it does that, this is a non-volatile RAM, NVRAM, and it's permanent. Then we'll move on to step 11, which is going to be the reload, as soon as we get a prompt. There it is. And that command is as simply, as is put there, reload. It's going to ask for a confirmation, so we'll provide the confirmation. At this point, you can jump for joy. If you start dancing now, though, it will be a moment, because this router is going to take some time to reload and get itself back up to the prompt that we need. But that is it for configuring from this mode. Whoa, did you see that? I've been experimenting with the process of speeding up time, and I think I just did it. Either that or I stopped taping and I started again after the boot process was completed. You be the judge of my magical ability. All right, in this nugget, We started off by looking at connectivity. We looked at the devices involved, the cabling involved, and the software packages and the terminal emulation packages that we're going to use. We also talked about ROM monitor mode, the fact that it's a low-level command mode that's used to resolve problems. And it's only used if we can't find the iOS as far as accidental use, but you can get there purposely by adjusting the configuration register to 2142. We also studied the break sequence, had an understanding that a break sequence is different for each terminal emulation package, and there have to be some research there to understand which one we need to use with our package. And we ended up by looking at the recovery procedure, a very successful procedure, if I might say so myself, and we ended up with a little bit of magic. I hope this has been informative for you, and I'd like to thank you for viewing.